Hello everyone, welcome to another session. In this session we're going to look at the homework problem from last class. As we've seen, transportation problems are relatively easy to solve if we can arrange all of the relevant information in the correct format. So the key is essentially putting together the table that we saw yesterday, or in the previous session, sorry. In that table, you had your supply, your demand, and your fees for transportation. Remember, in a problem like this, there are three key points. One, we're trying to minimize transportation costs. Two, from each source, we know how much is being supplied. And three, at each destination, we know how much is required. So we have supply, demand, and our relevant information. So let's look at this problem in front of us. Coal is mined and processed at the following four mines in Kentucky, West Virginia, and Virginia. Here's the location: Cabin Creek, Surrey, Old Fort, McCoy. Here's our capacity: 90, 50, 80, 60, for a total of 280. So we have the capacity to produce 280 tons between those four mines. These mines supply the following amount of coal to utility power plants in three cities: Richmond, Winston-Salem, and Durham. And they supply 120, 100, 110 tons for a total of 330 tons. The railroad shipping cost per town for coal are shown in the following table. Also, shipments are prohibited from Cabin Creek to Richmond. So we have 7, 10, 5, 12, 9, 4, 7, 3, 11, 9, 5, 7. So we have, in this situation, what they've done is they've taken a relatively simple problem, exactly like the one we did yesterday, and they made it slightly more difficult by asking you to interpret the data. In this situation, the data was not outlined to us as clearly as it could have been. It's actually a much more complex situation. Not because it's difficult, but because they didn't exactly spell it out for you. Instead, they've asked you to interpret and put together a table of your own. So let's look at the information. The coal is mined and processed at the following four mines in Kentucky, West Virginia, and Virginia. This is not important. One of the things they've done is they've attempted to confuse you by inserting place names that have no relevance to the problem. These are three places, yes, but these three places are not relevant because they're not sources. The sources are located in those three places. So our sources, we're going to make this black again because it's not important. We're going to make our sources, we're going to highlight them red. We have four key sources: Cabin Creek, Surrey, Old Fort, and McCoy. All four of these mines are located in Kentucky, West Virginia, and Virginia, but they're not critically important to the problem at hand. So what we're going to do is we're going to call it Cabin Creek Mine for clarity. Surrey Mine for clarity. Old Fort Mine, and McCoy So all four of these, the key information is not where the mines are located, but the actual mines themselves. So capacity, 90, 50, 80, 60, total of 280. This represents our supply. And again, supply, again, supply, and again, supply. Our total is 280 tons supplied. That's what this information has given us. Now, we also go down here. These mines supply the following amount of coal to utility power plants in 3 cities: Richmond, Winston-Salem, and Durham. These cities are the key. So our demand, similar, and this represents our supply. So now we see that the information is starting to come together. It was presented to us in a weird way, not weird, but in a way we hadn't seen before, in a more traditional format. Usually it's not generally spelled out for you as plainly as it has been in the past. So we have 280 units supply. Oh, and I did something silly. These aren't supply, these are demand. My mistake. So we have a total of 280 supplied, and we have 330 demanded. So right away, we can see there is one wrinkle. One thing that we haven't seen yet that might cause us a little bit of problems, and that's quite simply, we have more supplied, or not enough supplied, as we have demanded. So what we're going to do now is we're going to look down. The railroad shipping costs per ton for coal are shown in the following table. Shipments are prohibited from Cabin Creek to Richmond. This is a key point that we saw in the last session's question. If something is prohibited, we have to find a way to make that impossible for the computer to interpret. Now we have these key points down here. But as I said before, what we're attempting to do is recreate the table given to us previously. If we recreate that table, questions become very, very easy. So that's what we're going to do now. We're going to come down here and we see all of our relevant information. So these are our sources. Cabin Creek Mine, Surrey Mine, Old Fort Mine, and McCoy Mine. From our sources, we also have destinations. And here we see destination 1 is Richmond. Destination 2 is Winston-Salem. And destination 3 is Durham. So what we've done is we've rearranged this information here into our information here. And we'll go one step further, and we'll call this supply. We'll also go one step further, and down here, we'll call it demand. We're slowly recreating from the information given to us here the correct table as it should be displayed down here. So Cabin Creek to Richmond is $7. Cabin Creek to Winston-Salem, $10. Cabin Creek to Durham, $5. From Surrey Mine to Richmond, it's $12. Why does that do? From Surrey Mine to Winston-Salem, $9. And from Surrey Mine to Durham, $4. From Old Fort Mine to Richmond, we have $7. Old Fort Mine to Winston-Salem, we have $3. And Old Fort Mine to Durham, $11. One last section, we have McCoy to Richmond, $9. McCoy to Winston-Salem, $5. And McCoy to Durham, $7. What we've taken is transported this chart here and we've added it to the correct chart. Not the correct chart, but the chart that's easy to interpret down here. Now we'll add in our supply as well. So from Cabin Creek Mine, we see 90 tons are supplied. From Surrey Mine, we see 50 tons are supplied. From Old Fort Mine, we see 80 tons are supplied. And from McCoy Mine, we see 60 tons are supplied. Done. We also have demand though, so we'll look up here. Richmond requires 120 tons. Winston-Salem requires 100 tons. And Durham requires 110 tons. So all of this becomes relevant information. We're going to highlight the key points. The only thing we'll leave unhighlighted, just for clarity when we're reading, are our actual costs for each route. Now, what we could do is we could list these. 7x1a. We'll do that over here. And what we've done is we've shown the alternative method here that we were using prior. And in this section, we were simply listing each of our 12 different variables. That's where we were showing each of our 12 different variables. Now, in that situation, that's a very long, time-consuming process. That's the sort of process that would take not a ridiculous amount of time, but then again, it's only 12 variables. If that was 100 variables, 10 by 10, which is not uncommon, that would take a really long time to write that minimization objective function. If we use arrays, as we've done down here, it becomes a much easier problem to solve. So what we've done is we've eliminated this needless information. We've entered this relevant information. We've entered this relevant information. And we've included all of this information not in our traditional objective function, but instead as a table presented here. The only thing we haven't yet written in is that shipments are prohibited from Cabin Creek to Richmond. So looking down here, from Cabin Creek to Richmond, the number is 7. We're going to change that to 100. Make it 1,000. We're going to change that to 1,000. It's not an accurate representation, but because that route can never be used, we're just going to simplify and ensure that it can never enter in to any equation. All right, hopefully everybody's clear now. When we come back in a moment, we're going to continue. I'm going to solve first in QM and then second in Excel. So very quick review. Here's our transportation problem, all the relevant information highlighted. And here is the table that we need to complete all of the relevant information. Hello everyone, welcome back. In this section, as we've done before in the past, what we're going to do is we're going to solve this problem using QM for Windows. Now, as we've seen before, this is not an overly complicated process. The reason being is transportation problems are very limited in when they can be applied. Remember, there are 3 rules. Number 1, it has to be a minimization. There is no possible scenario where we want to spend more money transporting something. We want to spend the minimum amount of money possible. As we've seen in various other parts of the class, transportation adds no value to a product. It is inherently wasteful. If we're adding information, or if we're transporting for more money than we possibly could, all we're doing is wasting that money. It adds no value to the product. And production operations management, service operations management, is all about maximizing efficiency. In the various different stages of product development, product shipment, product anything, we want maximum efficiency. This is where we find competitive advantage. The reason that ties into linear programming and everything else is that we are making optimal choices. And optimal choices are all about maximizing efficiency. So when we ship, we want it to be a minimization. Number 2, in this situation, we have a set amount of suppliers, and they supply X amount of goods. It doesn't vary. It's always a similar amount. It can change over time, but whenever we conduct the analysis, we're conducting the analysis knowing that our supply is set. Finally, part 3, our demand is also set. Like supply, it can vary over time, but when an analysis is conducted, it is conducted under the assumption that nothing changes. So, because we have those 3 very tight limitations, transportation problems are not always possible. They're used very rarely only in transportation situations. And so what we have is a very highly, tightly defined model. Because of that, when we're using QM, it's a very simple process because there is very little flexibility in the model. So let's have a look at that now. As before, we click on Module. Because it's a transportation problem, we click on Transportation. and we open a new file. Very simply. We're going to title it our coal example. Our number of sources we can see here, we have Cabin Creek Mine, Surrey Mine, Old Fort Mine, McCoy Mine. So we have four sources. Destinations, we have Richmond, Winston-Salem, and Durham. So we have 3 sources, and it's a minimization. So we click OK. As always, we're going to enter our key information in here just for simplicity. Source 1, Cabin Creek. Source 2, Surrey Mine. Cabin Creek Mine, just so we're clear. Old Fort Mine, and McCoy Mine. Now our demand, again, we have it because we've taken the time. When analyzing the problem, we took the time to do it properly. We took the time to write essentially all of the relevant information we needed in one place. So we can enter our demand right now. Richmond demands 120 kilograms of coal. Winston-Salem demands 100 kilograms of coal, or 100 tons, sorry. And Durham requires 110 tons of coal. Same for supply. Supply, we know Cabin Creek Mine supplies 90 tons. Surrey Mine supplies 50 tons. Old Fort Mine supplies 80 tons. And McCoy Mine supplies 60 tons. Now, one thing we're going to do now, we're taking a little break here just because what is the possible reason we have for always labeling our values? Always labeling our suppliers, our destinations, our constraints. The primary reason is management science or management scientists usually operate in the role of advisors, consultants. Very rarely, unless it's a small operation, are people in leadership positions conducting actual management science. Instead, it's usually people working below them who are conducting the actual management science. One of the reasons why we want to, or one of the reasons why we allow, or sorry, allow is the wrong word. One of the reasons why we, in this situation, label everything is because usually this is being used in a presentation. Generally, as a consultant, it's your job to present this information to leadership. And if nothing is labeled, all of these random numbers that we're inputting can become very confusing and very unclear for leadership. So let's enter our initial values. Richmond was 7. Winston-Salem was 10. Durham was 5. And as always, these represent shipping costs. From Cabin Creek Mine to Richmond, cost $7 per ton. From Cabin Creek Mine to Winston-Salem, $10 per ton. From Cabin Creek Mine to Durham, $5 per ton. We repeat the same with Surrey. $12 per ton, $9 per ton, $4 per ton. Old Fort Mine again, $7 per ton, $3 per ton, $11 per ton. McCoy Mine, $9 per ton, $5 per ton, $7 per ton. Now we saw in our initial situation, shipments are prohibited from Cabin Creek to Richmond. That is why down here, we changed it to 1,000. That is why up here, we're also going to change it to 1,000. With any management science problem, one of the initial problems we run into is we're often unsure if we've arrived at the correct answer or not. The reason is we don't have a lot of ways to double check our work. Now we can use multiple programs, and that's one of the reasons we've done that. Another thing we can do is we can look at what we've done. So in this situation, let's have a look. We see that from Cabin Creek, Winston is 10, Durham is 5, Richmond is 100. Cabin Creek would most likely ship their entire supply where? Looks like Durham. It looks like they're going to send their entire supply to Durham. It's significantly cheaper for them to ship to Durham. Let's look at Surrey. Surrey is also really cheap in Durham. So if they send 90 and 50, that's 140. It looks to me like Durham will receive most of their coal from Cabin Creek and Surrey Mine. We don't know yet. We haven't conducted the analysis. But it looks that way because it's cheap here and cheap here. Old Fort Mine looks like of their 80 produced, probably a lot of it's going to go to Winston. It's really cheap. Compared to Richmond and Durham, it's very cheap for Old Fort Mine to ship to Winston. McCoy Mine is again cheap to send to Winston, so probably this 80 and 60, a good part of this will go to Winston-Salem. Now, Richmond requires 120. Old Fort Mine is good. McCoy also isn't bad. So they might get some of this as well. They're not going to get anything from Richmond. That's how we've eliminated Cabin Creek Richmond. But it looks like they'll probably get from Old Fort and McCoy. And finally, Durham. We covered Durham and Winston. So we're not sure yet, but we've looked at it. We've had a brief look. Let's see if our results are similar to what we expect. So all of our relevant information's been added. We hit the solve function. And we see here, Durham, as we suspected, gets all of their coal from Cabin Creek and Surrey. Winston, as we suspected, gets all of it from Old Fort and McCoy, and Richmond kind of gets the leftovers. 40 from McCoy, 30 from Surrey. So without knowing 100%, I can tell you this is 100%, but without knowing 100%, we see that our answers look kind of what we expected them to look like. So we probably can assume that this answer is correct. It looks like Durham receives 90 tons from Cabin Creek and 20 tons from Surrey. Winston-Salem receives 80 tons from Old Fort Mine and 20 tons from McCoy Mine. Richmond receives 30 from Surrey Mine, 40 from McCoy Mine. The dummy account in this situation is kind of the leftovers. It's filling in from leftover situations to try to give Richmond as much as what they require. Or in this situation, that's what it was over here when it was demand. Here, it's telling us if there's a dummy account. What do we think this is telling us? What it actually is telling us is that Durham has received what they require. We look down here, they required 110, they received 110. Winston-Salem required 100, they received 100. Richmond required 120, they received 70. So what we can see in that situation, what we're doing is we're showing over here that we are 50 tons short in Richmond. If our dummy account was on this side, as I said earlier, this is where the leftover goes. If it was excess supply, the leftover would go here. Because it's excess demand, it's excess demand, they're demanding more than exists, we're going to have shortages here. So if the dummy is on the bottom, it represents shortages. If the dummy is on the side, for suppliers, it represents excess. In our situation, we have 50 tons more required for Richmond. Winston-Salem is okay, Durham is okay, Richmond is not okay. This transportation problem represents a value, our transportation costs are going to be $1,590. Now, why did we shortchange Richmond? Winston got everything, Durham got everything. In a fair world, wouldn't we just divide that 50 between all three to ensure that everybody's just a little bit below what they require? That is a decent argument, but it doesn't represent the cheapest possible situation. What we're focused here is not fairness, not equality, not opinion, and not bias. Instead, we're focused 100% on the correct, cheapest possible optimal solution. And this is what it is. Hopefully everybody's been following along. Let's take a short break while I load the next relevant spreadsheet. And then we'll try to solve this again one more time in Excel. Welcome back, everyone. I now have the Excel spreadsheet set up. So what we're going to do is, as always, start with our coal example. And here again, what we're going to do is, as before, with any transportation problem, what we want to do at this point is set up our arrays. So let's begin with that. In this situation, we have first, we'll start over here and we'll mention our destinations. And again, all we're essentially setting up, is this table here. If we set up this table, these problems become very easy to solve. So destination 1 is Richmond. Destination 2, Winston-Salem. Destination 3, Durham. Now we have our sources. Cabin Creek Mine, Surrey Mine, Old Fort Mine, McCoy Mine. And we also have demand. We're going to list that down here. So demand is 100. We'll leave that out for now. And here we have supply. So we can begin entering our relevant information. So demand is 120 units demanded in Richmond, 100 units demanded in Winston-Salem, 110 units demanded in Durham. Supply is 90 in Cabin Creek, 50 in Surrey Mine, 80 in Old Fort Mine, and 60 in McCoy Mine. So this information has been given to us. This we're going to leave empty because these represent our decision variables. This is what the computer runs permutations of in order to determine what our optimal solutions will be. So we're going to leave them empty for now. Next, we're going to go down here and we're going to say amount received, and over here, amount shipped. And very simply is equal to these three, not equal to those, equal to the sum of those. And we're going to fill that down for all 4 suppliers. Over here, we do the similar thing, equals amount received, sum, and we add these up. And again, we fill right. Okay, moving on. These are the key points down here. And what we're looking for is our total cost. But we can't enter our total cost yet because we haven't written in our second array. That's what we'll do now. First, we'll minimize some of these columns to make things a little more clear on our miniature spreadsheet. Over here we have destinations, Richmond, Winston, Durham. Back. Sources, we have Cabin Creek, Surrey, Old Fort, and McCoy. All of the extra information isn't necessary because this merely represents our pricing table. So we fill in the relevant information. Make these a little smaller just so we can see everything. Here, Surrey is 12, 9, 4, 7, 3, 11, 9, 5, and 7. So we have both of our arrays. We have array 1 here and array 2 here. They're always going to be equal to each other. Our sum product function only works if it's the same amount of rows and columns in both arrays. So we'll come down here and we'll add in our final, our total cost formula. So our sum product, and sum product one more time represents this times this plus this times this plus this times this, etc. Same as we've done here, but we've just made it easier to input in a spreadsheet. So sum product is array number 1 is B5 to D8, comma. Array number 2 is I4 to K7. And we'll close our brackets. Those 2 arrays represent our multiplication. We find our total cost by multiplying these numbers times the amount shipped. The amount shipped we don't enter, we allow the computer to find. Once the computer has found these values, it multiplies them by these prices. Once it's multiplied by these prices, it then inputs our total cost. So we hit enter. Right now it will be 0 because nothing's been shipped. And then, as always, we enter our solver function. So this is a little big, one second. Oh, I can't minimize it. So our set objective is not B12, it is B11. As always, because it's a transportation, maximizing is impossible. We have to minimize. Changing variable cells. This is where we enter our first array, the array that the computer will find for us. Okay, so we're entering these 12 cells. The computer will run permutations for each of those 12 cells until it has satisfied our constraints. When it has satisfied our constraints, then it will check the price. For each time it checks the price, if it's a higher price or a lower price, it will continue selecting the lower price until it has found the lowest possible price that satisfies all of our constraints. So now we make it simplex LP, and we're going to add in our constraints. The first constraint is the amount shipped. Now, in this situation, do we have more or less available for supply? We have less. So it must be less than or equal to the amount supplied. Sorry, my mistake. We have not enough supply. So in that situation, we can make it equal to, or we can make it less than or equal to. Both would be okay. Because we know we have less supply than demand, we know all of this is going to be used. We cannot leave any at any of the mines. We require everything, and we still don't have enough. So in that situation, we know less than or equal to works, so does equal to. For simplicity's sake, we'll go less than or equal to. And then we list our supply. And what this says is the amount shipped must be less than or equal to the amount we have available. Now, in this situation, we know we're going to ship all of it, but this equation, the way it's set up, is no problem. So we add that, and we add our second one. And that is the amount received must be. And if we try to make this equal, it will not work. If we try to make it greater than or equal, it will not work because we do not have enough. So it has to be less than or equal to the amount demanded. We hit OK, and we've completed the problem. So we hit solve here. Solver found a solution. All constraints and optimality conditions are satisfied. We hit OK. Oh, 1 second. Okay, welcome back, everyone. Sorry, I made one small mistake there, and it was my fault. Sometimes with different versions of Excel and different versions of Solver, they process questions differently. So what we have to do when we add our constraints is we have to make the amount shipped must be equal to the amount supplied. If we don't make it equal to it, we'll make it 0 because that's cheaper. in this version. And again, we have to make the amount received less than or equal to the amount demanded. So the amount received less than or equal to the amount demanded. We hit OK, we solve, and we get these values. The exact same values we received earlier. The only difference is we do not have a direct reference to how much we're missing. We have to look and see that we're 50 short over in this section. So hopefully everybody's clear. In the next section, we're going to look at a new type of transportation problem. This is a base transportation problem. Hopefully everybody's clear. If you have questions, as always, feel free to ask me. See you in the next section.